So, so one of the conclusions that I've come to in the last couple of years is that scientists with data really aren't exposed to the concept of narrative. And it wasn't till I did some projects outside of the biology and neuroscience that I was trained in that I really began to understand how exposure to different concepts and different data can really change how you view the world. So those of you who know me know that I have a heavy interest in microscopes and neuroscience, but that I also spent about 5 years working in Afghanistan. And it was my experiences in Afghanistan that really got me to appreciate narrative and how it's different for different people. And so this letter was a letter that was written by local tribal leaders in a valley of Afghanistan to the commander of the local military base. And they wrote two versions, one in Pashto and this one in English. And if you read through it, they're talking about something that's happening, something involving a river. They have parables or proverbs. There is darkness under the flame of the candle. And then they go on and they talk about poppy cultivation and how they want something done. And then the last sentence is, hope government officials would act upon and seek any sensible solution way in case of hesitation. We are obligated to struggle properly in order to gain our rights. Which coming from tribal leaders on the border of Pakistan in a contested area with the Taliban is a threat to take lightly, or is not a threat to take lightly. But when you read through this in the narrative that comes from the Afghan elders, it's not entirely clear what it is that they want. And because this is the style of communication that they have. They get together, they write a letter, they put in some proverbs, they all sign it. And so I got involved in this trying to understand what the problem was. And so I went over to the village and walked along the river, just taking photographs, geotagged photographs of what they were saying the problem was. And then I got back to my computer, and so the problem was that the course of the river was changing. And they were blaming a Japanese NGO for doing river construction upstream for this river change. So when I got back to my computer, I pulled the photos in, and so you can see these icons are where I was taking photos of the river damage. And at first blush, I thought maybe the GPS coordinates were off because those photos aren't on the riverbanks. So what I did is I went and I got through some sources. I got some more current satellite imagery so that I could just verify and compare it. And then when I pulled up the new satellite imagery, you can see very clearly that the course of the river has changed. And so to a Westerner who thinks in terms of data and maps and visualizations, this makes a lot of sense to me, and it made a lot of sense to people who are to Americans who are on the military base, so I could point and say, this is the problem. Now I'm not making any claims about whether who did what in that situation, but the addition of a few different data points and some satellite imagery was really able to communicate clearly what it was that was going on. We also went over and looked at the construction that the Japanese were doing, and so this is the old satellite imagery, and there are irrigation ditches that are peeling off from the river. The Japanese group that went in, what they did is basically they put in a berm to get the water level up to put more water down the irrigation ditch. In doing so, ended up pushing the river off to the side. And the experience of being involved in this and using a little bit of data to put together a narrative and help deconflict the situation really convinced me that it's worth thinking about the problem that you're doing and the facts and events that you're trying to tie together with the way that you present your information. Which leads me into my real life's work, which is biology, and specifically microscopy. microscopy is one of those fields that has not really changed much in 100 years at least. Over on your left is Ramon Cajal, who's he's the most famous neuroanatomist and the person who's responsible for our understanding of neural connectivity and the idea that thoughts happen because they get transmitted down nerves. And so this is him at his desk in 1887. And then if you go to the desk of a pathologist today, that's what they look like. It's functionally the exact same user interface that has been used, that Ramon Cajal is using. And the most common stain, H&E, which is this stain in the background here, was invented in 1790. And it remains today to be the most common stain used by pathologists. And so I think that this is a problem because biology structurally is in 3 dimensions. And so I've been putting a lot of work into developing a 3D microscope, which changes the way that the data is collected from the microscope. Instead of slices being taken, put on glass slides, and then put into a microscope, the whole thing is automated, and we image it while we're slicing. And I won't dive too deep into the details, but in the center diagram, that wedge-shaped object is a diamond knife. We put light through the back of the knife. Since it's a diamond, we can see through it. And then we have an objective that's focused on the bevel of the knife. And then we image a single line of pixels continuously while the knife slices. And so that allows us to automate this process and to collect very large numbers of slices. And so what comes out, actually I've got a big one here. What comes out are very large numbers of images. To give a sense of scale, a modern pathology lab with high throughput equipment can process about 40 slides per hour. Our microscope can do about 3,600 slices per hour. And so being able to image with that speed on that scale allows us to build these very large 3D representations, which brings me into this problem of how do I present data to doctors and scientists so that we can get across the narrative that's happening. Now this is kind of an open question. A lot of this work is still ongoing, but the first things that we do are pretty simple. So like at the top we have a table, and so we segment and reconstruct the structures, and then we count things. And then we put in a table like the total surface area of the vasculature in this system is this amount. Then we can compare it to them. And that's really useful because like in a drug validation study, you want to have like hard numbers in a table that you give to the FDA. And so for some of our people, that's all they want to see is like the 2 things that compare their thing versus another, so they can say their thing is better. We can also do some more advanced visualization. So in the bottom here, that's a vasculature network where we've gone through and we've color-coded the structures by the radius. And so in addition to just seeing the structures, you can also see based on color some feature of it. I consider these pretty simple and unexciting. Hold on. But we've been experimenting with other ways to show people the data that we're getting from the microscope. This is a prototype built by a friend of ours, Charles Van Norman, who also I believe worked with Alex Peak on his project. We use this is built on Unity, the same system. But what we're in here right now is we're inside of the microscopy data coming out of our machine, and we're in a little game. And so we've got platelets and white blood cells that are running by. I'm not very good at flying this while looking backwards. And so we have, and so Charles has put in here a plaque that we need to hunt down. Now, I don't know that I would give this to a doctor and tell them this is their user interface that they're going to use for doing cancer diagnostics. But but it is for us. It's exploring what the actual possible ways to interact with the data might be. So with this one, with this one, what we're doing is trying to shoot them and get rid of the plaque. And so it might be good for educational purposes. But one of the things that's also good about this is that gaming interfaces are intuitive for an emerging generation of scientists and doctors who already know the key commands for navigating three-dimensional worlds. And so there's not collision detection isn't built into this yet, so we can just fly through the wall, and then we can be out amongst the rest of the vasculature, and we can use this to go through and examine vascular features. A big moment for me playing with this data was I actually found some artifacts in our data that I had never found, and this is one of our canonical data sets that we work with a lot, and that I had never seen that artifact before was sort of surprising. But when it's in a video game, I spent more time going through my own data just because it was in a video game interface and more accessible. Running low on time, so I'll flip to the next one. So there are other people who are working on interesting microscopy interfaces. So this is a really cool project by Sebastian Sung. It's a browser-based neural reconstruction program that has a gamified user interface. So basically, you're going through here and you're working with an AI system to go through and label neurons in the reconstruction. And every time that you do so successfully and that gets verified, you get points, and so they have a leaderboard. And so you can look and see, how you compare to the other people who are working with this 3D microscopy data. And so this is the other interesting example of people taking an innovative approach at how do you get people to interact with microscopy data. And the thing I think is cool about this is you can go through and you can look at the results in 3D alongside the classical two-dimensional representation of it. And I think it gives you, being able to look at both of them gives you a much better feel for what it is that you're actually looking at, as contrasted to just a flat two-dimensional view. And so to wrap up, I want to give thanks to my team. This work wouldn't be possible without them. And do we have time for questions?
Yes, we have, I think, a couple of minutes.
We do.
Okay.
I think Natasha needs to go, so maybe
I have 5 more minutes.
Okay.
So yeah, let's give Todd a couple.
Cool.
Do we have the mic? Oh, there. Okay, there we go. Yeah, I'll take it. Thank you. Questions? You've stunned them with your visuals. Okay, yes.
So you showed in your pictures an angstrom measurement. We were talking a little bit about this last night at the party.
Mm-hmm.
You were showing there was like a 20 angstrom. You're showing things much smaller than that in the vasculature.
Mm-hmm.
And angstrom's an atom. So how close is the imagery that 3scan provides to maybe not showing individual atoms, but things that are as small? I mean, those are things that are just 10, 20, 50 atoms apart.
That was a mu, so those are microns.
Oh, sorry, those are nanometers.
Yeah. So the resolution of our microscope is each voxel is about a cubic micron. So we're considerably larger than an atom. And there are, though the visualization I showed you from Sebastian Sung's group, they're doing electron microscopy, so they're able to do voxels down to the 10, 20 nanometer level.
Okay, cool. And do you see the possibility to collaborate? I've been following the life of the cell and the stuff you've been doing, and I'm super stoked to hear you work with Charles, because Charles works at the ENCODE group.
Yeah.
And do you see the possibility for what what ought to happen is a commons of the visualization and simulation techniques that we're all developing.
So I actually deleted a slide that maybe I shouldn't have, because I was trying to trim down the time. The last slide that I had was on things that I think we should be doing as a community to help make this these kind of projects work. And so the two things that I'm a big advocate for at 3Scan are open source software and open licensing on data. And we're going to be putting out openly licensed data sets so that people can take our data sets and use them. If Charles wants to build an educational video game, he can take our vasculature data set, put it in his video game, and we've got like a smooth transition on the data rights. And we're also, at 3Scan, we see software as an enabling technology, not something that we're trying to have a monopoly around. And so we're open sourcing all of our software so that anyone who wants to work with our data has access to the full tool set. So we're actively trying to figure out how we can get data out of our silo and into others. And we see gaming as a really cool, and education as a high potential area. So if Harvard or I forget which university it was, if they wanted to take our 3D data and use it in an animation or visualization or video game, from our perspective, that's awesome, because from our perspective, that actually just increases demand for high quality three-dimensional data.
Thank you, Todd.